Now that we have our steps of how to find the area under a curve, we're going to take those steps to go find the area of under a curve. We're going to find a finite area, an estimated one, which means we're just going to use the first 4 steps and use a Riemann sum to find using a set number of rectangles. So here's our first example where we're going to use our first 4 steps. So we're not going to use the 5th step because we're not going to find the exact value. We're not going to take the limit, but we are going to just find an estimated area based on what we're asked for here, which is that we have 4 rectangles. So that tells us that n equals 4. And they gave us the interval 0 to 4, which tells us the a equals 0 and b equals 4. Do it 3 times, once for left, once for right, and once for midpoints. So starting with part A, that's the left endpoints. So what does that look like on our rectangle, or on our graph here? Let's see, well, I'm splitting into 4 rectangles. I'm sorry, that's the wrong 4. 4 rectangles from 0 to 4. So there's my area of interest in here. And I want to split it into 4 evenly spaced rectangles. So if I have a base of 4 of this whole area, then I'll just split that into 4. So 4 divided by 4 is 1. So that means my delta x, that's the width of each rectangle, is b minus a over n, which b is 4, a is 0, divided by the number of rectangles, which is 4. So 4 over 4 equals 1. So the width of each rectangle is going to be 1 unit. So I'll mark my little rectangles here. So this is my delta x right here. And then I have another delta x here, and so on. Okay, now I need to figure out what the height is. So I have the base of the rectangle is 1. I need to find the height though. So to find the height, and we're going to do left endpoints, then that means for my height, I'm going to look at the left endpoint of each rectangle. So if one rectangle is in this first interval from x0 to x1, and this will be my x2, my x3, and my x4, which is b. Height of the rectangle will be the left side of each of those intervals. So that interval from 0 to x1, I'm going to use the height of the function on the left side, which is actually at 0. So my first rectangle will be 0. My second rectangle, the height on the left-hand side of that rectangle is right here. And it hits the curve right there. So my left rectangle is right here. So that's my second area. My first area is 0. My third area I find by going to the left-hand side of my third interval, which is that interval. So that is right here. And I go up to the curve and over to make that third rectangle. And then my fourth area is, again, I'm finding the left-hand side of the curve. So I go to the left side of that interval, which will be at x3, and find the height of the rectangle as f of x3. Oops. So my xi's, I was using the left endpoint each time. So the left endpoint of my first interval is the a, or in this case, 0. the left endpoint of my second interval was 1. So how did I find these? Well, xi is equal to, starting at the a value, add delta x I times. In this case, our a was 0, and our I is an index, and our delta x, that's this 1 that we just found in the previous problem. So that's 1 in this case. Or the previous step. So our final xi is equal to just I. So I have 0, 1, 2, and 3. They're all equal to the index. So 0, 1, 2, and 3. So to find the height, I just evaluate the function, which was given to me up here. F of x equals radical x at each of those x's. So in general, I would write the function of square root of xi, and we found out that the square root, that xi, we found that in the previous step. For this problem, xi is just I. So that would be square root of, so our function of I is the square root of I, which is 0, square root of 1, which is 1. I'll just put that in. So square root of 0 is 0, square root of 1 is 1, square root of 2 is 2, and square root of 3 is square root of 3. Okay, so when I go to find my sum, it's actually going to, because the steps we wrote were for a right-handed sum, the only difference is going to be that this I was going to be I minus 1, because we're just moving backwards. So we're going to start at x0 instead of x1, and then we'll end at x3 instead of x4. So our sum is actually going to be the sum from I equal to 1 to n of the function evaluated at xi minus 1, because we're using the left-hand side, times delta x. So that is the left-hand side of each rectangle. So that's, the base of each rectangle times the hand side. So the left-hand side of the first rectangle is 0. And then the base is always 1, because that's our delta x. And then add the next one. The base for the second one is 1. The height times the base, which is 1. The base for the third rectangle, the height for the third rectangle is radical 2. And then our base. And then our fourth rectangle is radical 3, and the base. And when I add those together, I get 0 plus 1 plus radical 2 plus radical 3. If I put that into a calculator, I get approximately this. So again, this is an estimated, because as you can see from our rectangles in the picture, you can see that it's going to be, all the rectangles are actually below the curve. So there's all this space that we missed. So it is going to be an underestimate of our actual area. And we're going to use the same steps again to find the area again, but this time we're going to use the right endpoints, which means when I build my rectangles, I'm going to have the same intervals. So I'll actually go ahead and start with step 1, and then we'll build the rectangles in step 2. Well, step 1 is to find delta x, and since we still have the same b and a and n, we still get that same result of 4 minus 0 over 4 equal to 1. So each delta x is still 1 unit. So that's x1, x2, x3, and our x4 is actually b. And our x0 is actually A. And our area is from A to B, same as before. The difference this time is going to be in step 2 when I build xi, well actually step 3. Because now I'm looking at the right-hand side of each interval. So this first interval, I'm looking at the right side. Where does the right side of the curve hit on this interval? It hits right here. So that's my height at x1. So my first height is going to be at x1 instead of x0. So on my table, I write x1. When we were using left-handed, we used x0 as our first height. So our first height starts at x1 and goes up to the curve. And then that defines my rectangle, or the height of my rectangle. And then at x2, I start at x2 and I go up to the curve, and then that defines my rectangle. At x3, I use my right-hand side of the interval, and I go up to the curve, and that defines my rectangle. And at x4, I go up to the curve, and that determines the height of my rectangle. So there's my 4 areas. So there's area 1, area 2, area 3, and area 4. So we're essentially adding up those 4 areas. So what were the x's that we used? Well, it's the same calculation to find xi as we did before. The only difference is when we get to step 4, we will use the right-hand side of the x's, so that instead of using x minus 1, we'll use x. So our x's, we used our x1, x2, x3, and x4. And that formula is still the same, which we got just as we did above. We got I for the x. So the x is 1, 2, 3, and 4. Those are our x values. And then to evaluate the function at those 4 points, we get square root of 1, which is 1, square root of 2, square root of 3, and square root of 4, which is 2. Bringing us to step 3. Again, we have the same function, so we'll have the same result as we had in part A. So the function value is, at any point, is square root of I, which is what we just found, and the sum of those 4 points. So those 4 rectangles. So that is the sum from 1 to n, to 1 to 4, of the right side endpoint of each interval times delta x. So the right side sum, the f of right side we get in this column right here. So that's 1, and then delta x is always 1. We found that in step 1. And then the second rectangle is square root of 2 times the base of 1. And the third rectangle is the square root of 3 times delta x, which is 1. And the fourth rectangle has a height of 2 times the square root of the delta x, or the base of the rectangle. So that gives me 1 plus square root of 2 plus square root of 3 plus 2, which I can simplify to 3 plus rad 2 plus rad 3. And that's an estimate of the area. As you can see, our rectangles all go a little bit above the line, so it's a little overestimate. And this is our estimated area under the curve, which I can also put in a calculator to get an estimated decimal. So now I can see that my area is somewhere between my lower end estimate and my upper estimate. This curve is always increasing. You can see that all of our left rectangles underestimated because the curve is increasing. So it's increasing. So each of my left measurements hit the minimum of the interval. Whereas because the curve is increasing, my right intervals are hitting the top or the higher part of the curve. And that's because the function is increasing. So we might get better or more accurate result using midpoints. So with midpoints, let's go through those same steps so we can see them laid out. So that first step is to find delta x. Our delta x is going to be the same because our a is still 0, our b is still 4, and our n is still 4. So nothing has changed there. So each of my delta x's will be 1 unit. So I'll get x1 at 1, x2 at 2, x3 at 3, and x4 at 4. So also the same calculations for, actually, I'm sorry, we won't get the same calculations for xi, because for xi, we're actually doing we're going to hit in the middle of the intervals. So our rectangles are still in the same place. So at 1, there's my cuts, 1, 2, 3, and 4. But my x value is going to be somewhere in that interval. It's actually going to be the midpoint of that interval. So my first one's going to be at 1/2. My second one will be at 1 1/2, which is 3/2. So that midpoint of the rectangle, there's my rectangle, that midpoint will be what determines the height of my rectangle. So let me draw those in. The height of the rectangle will be at the midpoint. So I start at the midpoint and I go up to the curve, and that decides the height of my rectangle. So in my second interval, I start at the midpoint and I go up to where it hits the curve, and that determines the height of my rectangle. And then at the third interval, I start at the midpoint, I go up to the curve, and that's how tall my rectangle is. My fourth interval, I start at the midpoint, I go up to the curve, and that decides my fourth rectangle height. So now my areas are this. Oops. So I'll put the outside of the rectangles in a solid color, and the height is determined by that dotted line, the midpoint of each rectangle. So to get xi, generally speaking, it would be a plus the change in x. But if I want to get to my first xi should be 1/2. So I take my a and add 1, but then I subtract a half every time. So I take my delta x and multiply it by however many x's I've added minus 1/2. So that first xi becomes 1/2. The second one becomes 3/2. Now remember, a is 0, and delta x is 1. So that's I minus 1/2 And we can simplify that to just I minus 1/2. So when I is 3, I minus 1/2 is 2.5, or 5/2. When I is 4, our xi is 4 minus 1/2, which is 3.5 or 7/2. So there's our xi's. And now to calculate our function at xi's, we have the square root of what we got here, which is I minus 1/2. And from our table, we can see we just need to pick the square root of these 4 numbers, which is 1/2, square root of 1/2, square root of 3/2, square root of 5/2, and square root of 7/2. Bringing us to step 4 of just adding all 4 of these rectangles together. The first rectangle is height of square root of 1/2 times the base of 1. The second rectangle has a height of radical 3/2 and the base of 1. The third rectangle has the height of 5/2 and a base of 1. And the fourth rectangle has a height of 7/2 and a base of 1. When I add those together, I get a lot of square roots. Oops, this is a square root that goes over 2 also. In fact, all my numerators are square roots. So that's the square root of 1, which is 1, plus the square root of 3, plus the square root of 5, plus the square root of 7, all over square root of 2. And if I put that into a calculator, I get approximately 5.3838. Notice that is somewhere between our lower estimate and our upper estimate. So this isn't always the case, but on this particular function, it's always increasing. That meant that my left side limit turned out to be my underestimate. So on this function, L4 is an underestimate. Since this function is always increasing. So each time we took a left side rectangle, we take the minimum on that interval. And that, again, is because f of x is increasing, and that's why it worked out that way. Similarly, for the same reason, R4 is an overestimate. Again, since the function is increasing, so each time we take a right side limit, the right side is the maximum. On that interval. So most likely M4, the midpoint, would have been the best estimate. since it has a little bit of under and a little bit of over. From the midpoint graph, you can see there's, sorry, that's the wrong graph. On the midpoint graph, you can see there's a little bit of under space, but there's also a little bit of over space. Maybe those even cancel each other out. Actually, when we are concave down, like this graph is, you can still see that it's always going to be still a little bit of a overestimate, because we always have a little bit more on top because of the concavity than we lose on the bottom. So concave up, I still have a small overestimate, but much less than we did when we started here. So M4 is the best estimate because it has both underestimating rectangles and overestimating parts. However, since f of x is concave down, it will still be an overestimate. If it was concave up, we would get an underestimate. So since f of x is concave down, we still get a small overestimate.